July 10, 1942. Calcutta. Air Headquarters, India, Eastern Air Command. A staff officer places Operations Summary Number 118 on Air Marshal Sir Richard Peirse's desk. The paper shows a grim tally. 92 Allied aircraft lost in 4 months. Japanese night bombers strike unopposed over ports from Chittagong to Calcutta. The early warning grid consists of visual observers and sound locators, insufficient in rain and darkness. Commanders expected night operations to remain impracticable in monsoon conditions. Reality proved different. Japanese formations exploited cloud cover. Average scramble time, 42 minutes, far too long to intercept. In filing cabinets, requests already circulated for a technology most thought useless in tropical heat and humidity. Within 12 months, invisible waves would deliver warning times exceeding 20 minutes even in the heaviest monsoon rains. The enemy would blame lightning and navigation errors. The files would credit mathematics, maintenance, and a network built under conditions thought impossible. The monsoon of 1942 turned Burma's skies into a gray curtain. Rain fell in sheets. Clouds hung low over jungle and coast. Visual spotting became guesswork. Sound locators picked up thunder more often than engines. Japanese bomber crews understood this advantage. They flew at night, hidden by weather, striking ports and supply lines. Allied fighters sat grounded or scrambled too late. Losses mounted. Frustration grew among commanders who knew the enemy was coming but could not find them in time. Air Headquarters, India reviewed the numbers. 92 aircraft destroyed or damaged between March and July. Enemy raids succeeded because warning came too late or not at all. The existing system relied on human eyes and ears. Coastal watchers phoned reports when they heard engines. By the time fighters reached altitude, the bombers had dropped their loads and vanished into clouds. The gap between detection and interception measured in tens of minutes. In air combat, that gap meant death. Officers studied British experience. In Europe, radar provided early warning against German raids. Stations along the coast tracked formations far out to sea. Controllers vectored fighters to intercept. The system worked in temperate climates with stable power supplies and controlled conditions. India presented different challenges. Humidity reached 90%. Temperatures soared. Electrical infrastructure remained sparse. Monsoon rains lasted months. Termites ate through cables. Dust and moisture invaded equipment. Many doubted radar could function under such conditions. Yet the need remained urgent. Japanese air superiority threatened Allied ground operations. Supply lines depended on ports that enemy bombers struck at will. Without effective air defense, the campaign in Burma faced collapse. Commanders logged requests for radar equipment. Air Ministry files recorded the priority. 12 GL Mark III sets, 6 AMES Type 15 units for India. Shipment would come via Middle East convoys. No one knew if the equipment would survive the journey, much less the climate. Specifications promised detection ranges near 40 miles in good weather. Performance in 90% humidity and heavy precipitation remained unknown. The sets required stable 240-volt AC power. Generator capacity was scarce. Rail lines prioritized ground forces. Every resource faced competing demands. Installing radar meant diverting fuel, transport, and personnel from other needs. The gamble was significant. If the equipment failed in tropical conditions, the investment would be wasted. Air Headquarters, India minute dated July 31, 1942, stated the requirement clearly. Portable radar adaptable to tropical climates. Landline links to fighter control essential. 224 Group noted that coastal sectors lacked instrument meteorological capability. The institutional shift was underway. Radar gained priority not for strategic bombing defense as in Britain, but for forward tactical early warning in jungle and coastal sectors. Losses drove the decision. Numbers demanded action. Within months, the first sets would arrive. November 2, 1942. Liverpool Alexandra Dock. Cargo tallies listed magnetrons, valves, aerial masts, and spare waveguides. Approximately 500 tons of radar equipment loaded under convoy protection bound for the Indian Ocean. Among the crates sat centimetric prototypes from TRE Malvern, intended for field trials. The manifests recorded serial numbers and technical specifications. Dockworkers secured the loads. Convoy escorts prepared for the long voyage through submarine-infested waters. The equipment represented Britain's technological edge, now heading to a theater most considered hostile to electronics. The voyage took 26 days. Convoys zigzagged to avoid U-boats. Ships rolled in Atlantic swells, then Indian Ocean heat. Below decks, crates shifted despite lashing. Salt air penetrated holds. By the time ships reached Bombay on November 28, the equipment had endured conditions factory specifications never anticipated. Unloading began immediately. Indian stevedores moved crates to warehouses where tropical storage under canvas awaited. No climate control existed. Temperatures inside the sheds exceeded 100 degrees Fahrenheit. Humidity condensed on metal surfaces. Engineers from the Royal Corps of Signals and Indian Electrical and Mechanical Engineers examined the equipment. Factory manuals assumed stable mains power, controlled climate, and calibrated test benches. Bombay offered none of these. Power came from petrol generator fleets. Spare parts faced months-long backlogs. Workshops operated in heat that melted solder if left unattended. The gap between specification and reality was wide. Adaptation became immediate necessity. Transformers required rewiring for 220-volt DC generator output. Field repair protocols needed amendment. Humidity trials began. Sets ran for 72 continuous hours at 90% relative humidity after improvised drying procedures. Desiccant rations were issued per set. Valve survival depended on keeping moisture out of circuits. Engineers discovered that rice ovens could bake moisture from components. Workshop notebooks recorded the trials. Leakage tests showed acceptable performance after 24 hours of drying. Cabling presented its own challenge. Copper pairs needed protection from termites. Oil drum ducts provided armored sheathing. Burial depth specifications called for more than half a meter. Daily insulation tests became standard procedure. TRE circulars arrived with technical guidance. Field calibration must include temperature range correction. Apply plus or minus 2% echo strength adjustment. The instructions acknowledged that tropical conditions differed from laboratory standards. Procedures adapted to reality. Workshop notebook from Dimapur, December 18, 1942. Valve salvage via rice oven drying. Acceptable leakage after 24 hours. The improvisation worked. Equipment thought fragile proved reparable under field conditions. Maintenance crews learned to work with heat, humidity, and limited supplies. The theater once expected to destroy electronics became the testbed that extended radar endurance beyond European forecasts. Sets designed for Britain's climate now operated in monsoon jungles. The improbable became routine. By year's end, the first stations neared operational status. Masts rose along the coast. Generators ran test cycles. Operators trained on scopes and plotting procedures. The network was taking shape. Whether it could perform in combat remained to be seen. March 11, 1943, evening. Chittagong coast. AMES 15 number 39. An operator on night shift watched the scope. Rain drummed on the shelter roof. Visibility outside approached zero. The green glow showed clutter from weather, then something else. A slow maritime echo near Akyab, altitude indeterminate. The operator marked the bearing and range. The information went by landline to 224 Group Operations Room. Fighter control relayed vectors. A hurricane Peirse scrambled from the forward strip. Engines roared through rain. Pilots climbed on instruments. Ground controllers provided range and bearing updates over VHF radio. The fighters turned toward the contact. At 8 miles, visual acquisition seemed impossible. Rain obscured everything beyond the cockpit. Yet the vectors held steady. Controllers refined the intercept geometry. At 4 miles, one pilot glimpsed a silhouette against clouds. Tracers reached out. The contact broke apart. Wreckage was observed at dawn on the water. A Japanese reconnaissance seaplane. Engagement logged. 224 Group Operational Record Book. First radar-assisted kill in Eastern Theater confirmed by Coastal Patrol sighting. Air Ministry Summary Number 41 analyzed the result. Detection performance measured 37% above forecast in heavy rain after temperature gain correction. The theory worked. The equipment performed. The kill proved concept under the worst conditions. Radar and controller and VHF chain functioned despite monsoon weather. Japanese loss sheets compiled post-war noted the aircraft as failed to return, cause unknown, likely navigation error. Tokyo had no knowledge of Allied radar along the coast. The assumption remained that weather prevented effective night operations. That assumption just cost them an aircraft and crew. More losses would follow before understanding dawned. The invisible network expanded while the enemy attributed losses to weather, mechanical failure, and bad luck. The success validated months of effort. Equipment shipped from Britain, adapted in Indian workshops, installed along jungle coasts, now demonstrated combat effectiveness. Warning time made the difference. The hurricane pilots had vectors before they could see anything. Ground control positioned them for intercept when visual search would have found nothing. The kill ratio shifted. Attackers became vulnerable. Defenders gained advantage. Technical reports circulated through Air Headquarters India and back to London. Monsoon conditions did not degrade performance as much as feared. Temperature gain correction compensated for environmental effects. Proper maintenance kept sets operational. The theater was proving friendlier to radar than predicted. Lessons learned fed back into training and procedures. More equipment arrived. More stations came online. The network grew. By late March, 6 stations operated along the coast and forward sectors. Coverage remained incomplete but improving. Each station added depth to the defensive network. Redundancy increased reliability. If one set went offline for maintenance, others covered the gap. Controllers developed procedures for multi-station tracking. Plotting accuracy improved. False alarms decreased. Confidence grew among fighter crews. They trusted the vectors. Controllers proved their guidance worked. The first kill was proof. Numbers would follow. But on that March night, 1 operator, 1 controller, 2 pilots, and 1 radar set demonstrated that technology could overcome weather. The monsoon no longer belonged to the enemy alone. September 1943. Arakan Front. The arc from Cox's Bazar to Mongdaw. Dawn calibration cycle began at each station. Operators logged ambient temperature, valve anode currents, and background noise levels. Signal Corps teams checked continuity on underground lines. The plotting board at fighter control showed 28 active sites. Green lights indicated operational status. The network had matured. Commanders once expected fragmented coverage with gaps too wide for effective control. Reality proved different. Contiguous sector plots emerged from stations spaced for overlapping coverage. Average landline length measured 9 kilometers. 187 miles of cable-connected sites to control rooms. Redundancy came from parallel pairs. If one line failed, the backup carried traffic. Royal Corps of Signals line parties patrolled routes daily. Termite ingress remained a threat. Oil drum sheathing provided protection. Insulation tests caught problems before they caused outages. GL Mark III sets repurposed for inland use. Type 15 covered coastal and forward zones. Height finding used 2-station triangulation procedures. Daily meteorological and temperature logs supported echo strength calibration to plus or minus 2% accuracy. Plotting board standard operating procedures became uniform across sectors. Controllers spoke a common language. Plots moved smoothly from detection to handoff to interception. The system functioned as designed. Supply lines extended deep into jungle. Mule columns transported fuel tins over trails that disappeared in rain. Generator maintenance intervals were set to every 50 hours runtime. Technicians kept logs. Fuel consumption averaged 400 gallons per day across the network. 5-gallon tins moved by mule, porter, and occasional airdrop. The logistics were complex but sustainable. Radar required power. Power required fuel. Fuel required transport. The chain held. Signal Situation Report dated September 5, 1943. Continuity satisfactory. Termite ingress mitigated by oil drum sheathing. Controller's log. 3 night raids plotted. 2 broken off before initial point. The first measurable outcome appeared. Not aircraft destroyed, but raids that turned back. Enemy formations detected early changed course rather than press attacks. The statistic began to climb. Deterrence through detection. Knowledge of defense reduced enemy willingness to risk losses. Indian telephonists manned switchboards. Fighter control rooms operated around the clock. Training emphasized speed and accuracy. Correlation between coastal and inland posts reduced false plots. Post-action verification showed 94% accuracy. The human element proved as critical as the technology. Skilled operators translated raw echoes into actionable vectors. Without their discipline, radar was inert equipment. With it, the network came alive. The continuous network shortened mean warning time. Scramble efficiency rose. Successful enemy raids declined without proportional increase in air combat. Fighters flew fewer sorties but intercepted more often. Controllers directed aircraft to targets detected minutes earlier. The advantage compounded. Each successful interception reinforced confidence. Each deterred raid reduced enemy effectiveness. The monsoon war was shifting. Japanese formations still crossed the lines, but they no longer flew unopposed. Detection was certain. Interception probable. The calculus changed for enemy planners. Risk increased. Reward diminished. Air operations required reconsideration. Yet Tokyo remained unaware of the cause. Reports blamed weather, mechanical issues, and crew error. The invisible network remained invisible to those it opposed. March 1944. The Burma-India border, Chindwin crossings, Imphal Kohima sectors. Japanese 15th Army launched Operation Yugo. The offensive aimed to seize Imphal and drive into Assam. Air superiority was assumed. Weather and surprise would protect advancing columns. Field phones at Palal and Kohima radar posts clattered with alerts. Multiple tracks appeared on scopes. Controllers initiated sector-wide warnings. Ground crews started engines in rain. Fighters scrambled. Japanese General Renya Mutaguchi expected surprise. Allied 1943 scramble times suggested porous defense. Monsoon weather would hide his forces. Reality differed sharply. Average readiness time in March 1944 measured 14 minutes. All daylight raids were plotted before reaching forward positions. Surprise was impossible. Detection was certain. Interception followed. Number 11 Group RAF and Indian Air Force squadrons flew continuous operations. Radar plots converted to vector cards. VHF discipline enforced strict radio procedures. Night fighting bowfighters allocated to likely attack axes. Ground-controlled interception by standardized procedure, pending full AI airborne interception rollout. Height deconfliction via triangulation prevented friendly collisions. The system orchestrated defensive operations with precision that would have been impossible months earlier. Number 11 Group Diary A44/29. All enemy raids plotted. No daylight surprise achieved. The entry understated the achievement. Complete detection coverage meant Japanese air operations proceeded under constant observation. Formations detected on approach. Fighters vectored to intercept. Bombers harassed before reaching targets. The offensive depended on air support. Air support depended on reaching targets. Targets became harder to reach. Attrition accumulated. Japanese staff officers noted persistent leaks. Counterintelligence investigations began. The assumption was spies or informants. Reality was more prosaic. No human spies reported aircraft movements. Electromagnetic waves detected them. Landlines carried the information. Controllers vectored the response. The decisive leak ran through cables and cathodes, not human networks. Japanese security sweeps found nothing because they looked in the wrong places. Post-war Japanese notes reflected the confusion. Persistent leaks suspected. Recommend counterintelligence. The search for spies intensified while the actual mechanism remained unknown. Japanese doctrine assumed that monsoon weather protected operations. British radar converted monsoon from adversary to ally. Poor visibility aided defenders with electronic eyes. Enemy formations visible on scopes while pilots flew blind. The advantage was total and invisible. The campaign ground forward. Japanese advances met stronger resistance than expected. Air support proved less effective than planned. Supplies failed to arrive. The network that detected bombers also tracked transport aircraft. Interception extended to supply flights. Attrition affected logistics as much as combat operations. The offensive stalled. Impel held. Kohima held. Radar played its part in both outcomes. Allied casualties remained significant. Ground combat was fierce, but air superiority never wavered. Fighters maintained pressure. Bombers struck Japanese positions. Supply aircraft flew with acceptable loss rates. The network provided the foundation. Early warning enabled response. Response denied the enemy freedom of action. Denial created opportunity for Allied offensives. The virtuous cycle accelerated. By April, Japanese air operations over the battlefield declined markedly. The search for spies continued. The waves kept flowing. Detection remained constant. The invisible shield held. April 1944. Dimapur workshops. Forward maintenance. Workbenches stacked with failed valves. Lieutenant R.V. Wagh, Indian electrical and mechanical engineers, oversaw salvage operations. Drying cycles timed on improvised rice ovens. Spare parts logged against site returns. The workshop sustained the network. Without it, radar was temporary. With it, operations continued. 91% radar uptime in April despite humidity and supply disruptions. The figure represented thousands of hours of maintenance work. Fuel consumption measured 400 gallons per day. 5-gallon tins moved by mule across flooded tracks. Generator overhaul schedules were strictly enforced. Equipment that missed maintenance failed in the field. Discipline prevented failures. Failures disrupted operations. Operations saved lives. Valve salvage success rate reached 78%. Desiccant canisters regenerated after saturation. Cable faults traced by insulation megome tests. Battery-backed telephones maintained plot lines during generator swaps. Redundancy built into every system. No single failure cascaded into network collapse. Resilience was engineered, not accidental. Workshop log. Drying and rebaking achieved stable gain. Leakage within tolerance. Sector report. No radar outages exceeded 2 hours. Priority stores redistributed by air where possible. The numbers told the story. Operational availability drove interception outcomes. Interception outcomes shaped battlefield results. Maintenance determined availability. Technicians in workshops influenced battles they never saw. Spare parts arrived by convoy, by rail, by air. Priorities shifted constantly. Artillery complained of rationed ammunition. Infantry needed rations. Fuel-fed trucks and tanks. Yet radar stores flowed. The decision reflected understanding. Early warning multiplied the effectiveness of available fighters. Fewer aircraft achieved more when properly directed. The network was a force multiplier. Force multipliers deserved supply priority. Indian electrical and mechanical engineers' workshops operated at Dimapur and Pune. Royal Corps of Signals detachments provided communications expertise. Local porters and muleteers moved supplies forward. The network depended on diverse contributions. British engineers designed equipment. Indian technicians maintained it. Local labor moved it. Imperial hierarchy mattered less than functional cooperation. The network worked because everyone made it work. Improvised solutions became standard procedures. Rice oven drying of valves spread across workshops. Transformer rewiring for generator output was codified. Termite-resistant cable burial techniques documented. Field experience fed back into training. New technicians learned from veterans. Knowledge transfer preserved capability despite personnel rotation. The institution learned and adapted. Maintenance doctrine transformed imported sets into theater-hardened systems. Equipment designed for Britain now thrived in Burma. Specifications meant less than field results. Laboratory standards gave way to operational requirements. The transformation validated the investment. Radar worked in the monsoon because people made it work. Technology enabled advantage. People sustained advantage. Both were necessary. Neither was sufficient alone. Artillery did complain about rationed ammunition. Fuel was tight, rations sometimes short, but the radar board never went dark. That priority reflected strategic choice. Air superiority mattered more than marginal increases in ground firepower. The decision was defensible. Results supported it. The network delivered value exceeding its cost. May 1944, Tokyo Air Technical Bureau. Captured papers examined post-war. Summary tables listed Type A6 and Tachi 6 allocations. Approximately 12 sets for Burma theater. Notes mentioned meteorological interference and lack of centimetric capability. Japanese radar technology lagged Allied development by years. The gap was strategic, not tactical. Production limitations, not design philosophy, constrained deployment. Expectation in Tokyo held that British radar in India was non-existent or minimal. Intelligence estimates assumed tropical conditions prevented effective use. AMES-15 range to 130 kilometers with proper calibration contradicted those assumptions. Networked control rooms functioned across sectors. The expectation proved wrong. Reality remained hidden from Japanese planners until too late. Japan lacked cavity magnetron production before 1945. Reliance on metric band radars yielded coarse resolution. Allied introduction of short wavelength systems enabled smaller antennas and better clutter rejection. Technical advantage translated to operational advantage. Detection range meant warning time. Warning time meant interception opportunity. Opportunity converted to kills and deterrence. Operational numbers from March to July 1944. Japanese air losses approximately 404. Allied total approximately 156 across the theater. Loss ratios approached 3-1. Sustainability favored the side losing fewer aircraft. Japanese replacement pipelines strained. Allied production met demand. The arithmetic favored defenders. Captured memorandum post-war. Centimetric principle unknown to our development. Allied technical intelligence brief. Enemy radar effective range approximately 20 kilometers against medium bomber, insufficient for warning. The gap was fundamental. Short wavelength radar provided British forces with detection capability Japanese forces could not match or counter. Strategic technology lag became tactical blindness. Warning time deficit converted to airframe losses and failed raids. Production capacity constrained Japanese radar deployment. 12 sets for Burma represented significant allocation given overall production. The number was insufficient for network coverage. Individual stations operated in isolation. No integrated control rooms coordinated responses. Detection without networking reduced effectiveness. British system integrated detection, communication, and control. Japanese approach remained fragmented. Integration multiplied effectiveness beyond raw numbers. The shortage that mattered was not fuel but wavelength. Cavity magnetron technology enabled centimetric radar. Centimetric radar enabled better performance in clutter and weather. Better performance meant longer range and finer resolution. Longer range meant more warning time. More warning time meant more successful interceptions. The cascade started with fundamental physics and ended with destroyed aircraft. Japanese technical staff understood the problem too late. Development programs began but production remained years away. The war moved faster than development cycles. By the time improved radar reached prototype stage, Burma was lost and Japan faced defeat. Technology timelines constrained strategic options. Decisions made in 1941 shaped outcomes in 1944. The lag proved fatal. Post-war examination revealed the extent of the gap. Allied investigators found Japanese radar primitive by comparison. The conclusion was stark. Technical superiority in detection translated to operational dominance in the air. Physics shaped outcomes as much as courage or tactics. June 1944. Kohima Ridge, Sector Communications Center. Switchboards glowed in dim light. Indian telephonists relayed plots. Controllers updated grease pencil tracks on plotting boards. A small notebook bore signature Kalyani Mukherjee. 118 alerts in 1 month. The network breathed because people sustained it. Technology alone was insufficient. Human skill translated potential into performance. Plotting board drills every 6 hours maintained readiness. Speed and direction estimation rules standardized across control rooms. Correlation with coastal and inland posts reduced false plots. Accuracy verified 94% post-action. The procedures worked because people followed them. Discipline enabled precision. Precision enabled timely interception. Interception saved lives and destroyed enemy aircraft. Notebook entry. Rain louder than guns, yet echoes steady. The observation captured the paradox. Surface conditions were impossible for visual operations. Underground, electromagnetic signals traveled unaffected. Technology bypassed weather limitations. Human operators made technology useful. The combination was decisive. 224 group roster showed communications staff exceeded 60% Indian nationals. The number reflected reality. British officers commanded. Indian personnel operated key systems. Telephonists, radar operators, and technicians sustained the network. Empire's structure was hierarchical. Operational necessity was pragmatic. The network functioned because it incorporated personnel wherever skills existed. Controllers assigned vectors. Operators tracked targets. Telephonists relayed information. Technicians maintained equipment. Line parties repaired cables. Fuel crews moved supplies. Each role connected to others. Network theory was literal. Physical networks of cables and sets. Human networks of trained personnel. Both necessary. Both effective. Integration multiplied value. Skilled communications translated echo to actionable vector. Without training, radar produced raw data. With training, data became intelligence. Intelligence enabled decision. Decision directed action. Action produced results. The chain held only if every link functioned. Weakest link determined overall performance. Training and discipline strengthened each link. Fighter crews trusted controllers. Trust developed from successful interceptions. Success developed from accurate vectors. Accuracy developed from skilled operators. Skill developed from training and experience. The foundation was human, even when the technology was electronic. Aircraft and radar were tools. People wielded tools. Outcome depended on both. Empire's invisible empire was manual skill. Thousands of hands behind each interception. The cliché captured truth. Radar screens, plotting boards, telephone exchanges, maintenance workshops, fuel depots, cable trenches. Each required human effort. Effort sustained operations. Operations delivered results. Results shaped campaigns. Campaigns determined outcomes. The chain extended from technicians' workbench to strategic victory. No single individual determined success. No single technology guaranteed advantage. Integration of systems, procedures, training, and personnel created effectiveness. The network was greater than its parts. Synergy was real. Documentation showed it. After-action reports confirmed it. Statistics verified it. The invisible shield was collective achievement. Rain fell for months. Operations continued. Alerts numbered in thousands. Interceptions in hundreds. The routine was grinding. Personnel rotated. Fatigue accumulated. Yet performance remained high. Institutional knowledge preserved capability despite turnover. Procedures documented. Training transferred skills. The network endured because it was designed to endure. Resilience was engineered into structure and doctrine. Kalyani Mukherjee's notebook recorded 1 month. Multiply by months of operations. Multiply by number of personnel. The aggregate effort was enormous. The result was air superiority that enabled ground victory. The contribution was recognized by those who understood. History recorded the outcome. Memory honors the effort. July 15, 1944, 22:40 to 23:55 hours. Akyab, Station J27, 224 Group. Scope showed 18 bogies at approximately 230 miles, inbound. Controllers assigned number 177 Squadron Beaufighters to intercept. Height determined by crossfix from multiple stations. Fighters climbed through cloud on instruments, visibility less than 300 yards on the ground. Ground-controlled vectors guided aircraft toward contacts. AI airborne interception Mark 8 present in some aircraft. Merges at approximately 8 miles on airborne radar. VHF radio telephone for final turn guidance. Searchlight control Mark 3 queued to predicted tracks to disrupt low-level egress. The integration was complete. Ground radar, air radar, radio, searchlight, procedure, training, all elements synchronized. Contact, tracers, bombers shattered, 11 destroyed, remainder scattered. Some jettisoned bombs over water. Others turned for home. The raid collapsed. Air Ministry Cable AM3127. First radar-controlled victory achieved in full monsoon conditions. Japanese report annotation. Lightning suspected. The explanation was wrong. Lightning did not systematically destroy multiple aircraft. Fighters did. Nature blinded pilots. Radar replaced eyes. The method was repeatable. Not lucky night. Operational procedure. Proven under worst conditions. Confidence solidified. Controllers knew the system worked. Fighter crews trusted vectors. Enemy planners faced untenable situation. Raids proceeded into effective defense. Losses mounted. Results diminished. The calculation turned against continued operations. Night of July 15th became reference point. Proof that monsoon no longer protected attackers. Weather that once aided enemy now aided defenders. Technological advantage reversed environmental effects. Physics and engineering overcame meteorology. The accomplishment was profound. Conditions thought prohibitive proved manageable. Equipment thought fragile proved robust. Network thought impossible proved operational. The victory was collective. Radar operators detected contacts. Controllers computed vectors. Pilots flew intercepts. Ground crews maintained aircraft. Technicians kept sets operational. Fuel crews delivered supplies. Each contribution necessary. No single element sufficient. Integration delivered result. The network functioned as designed. Design reflected understanding of requirements. Requirements derived from operational experience. Experience fed into improved procedures. Improvement compounded over time. Japanese bomber crews returned to base shaken. Reports described impossible conditions. Fighters appeared in darkness and cloud. Interception was precise. Escape difficult. Morale suffered. Leadership questioned raid value. Attrition exceeded acceptable levels. Risk outweighed potential gain. Operations curtailed. The deterrent effect exceeded direct kills. Raids that never launched cost no defenders' lives. Prevention through presence. Capability demonstrated through successful engagements created reluctance to engage further. Number 177 Squadron logged 11 confirmed kills. Individual pilots received credit. Squadron history recorded the action. Awards followed. Public recognition went to aircrew. Behind them stood the network that made success possible. Recognition was incomplete but inevitable. Fighters were visible. Radar was secret. Secrecy precluded public acknowledgement. Classification lasted years. History eventually recorded broader truth. The night of July 15th validated years of effort. Equipment shipped from Britain. Adapted in India. Installed in Burma. maintained under impossible conditions, operated by trained personnel, integrated into effective defensive network. Result: air superiority in monsoon conditions. The achievement redefined what was possible. Limits once thought absolute proved surmountable. Engineering and determination overcame environment. The lesson extended beyond radar to broader questions of capability and will. August 1944. Rangoon Experimental Research Section. Japanese technician notes showed spark gap transmitter tested for interference. Measured power less than 0.5% of Allied cavity magnetron output. Effect negligible beyond yards. The attempt was logical. The execution was futile. Technical capacity constrained countermeasures. Strategic gap prevented effective response. Expectation among Japanese engineers. Simple jammers or chaff substitutes might degrade British radar. Reality. Lack of centimetric understanding and insufficient output power rendered efforts ineffective. Spark gap transmitters generated broadband noise. Effective jamming required power exceeding target radar by significant margin at the receiver. Japanese equipment produced milliwatts. British magnetrons produced kilowatts. The ratio made jamming impractical. Allied AI Mark 8 expanded look-ahead detection to approximately 8 miles. Night fighter doctrine refined for Burma terrain. Interception success climbed from 56% in June to 82% in September. Sortie effectiveness recorded in group summaries. The improvement reflected experience, training, and equipment reliability. Each factor reinforced others. Positive feedback loop accelerated improvement. Effectiveness compounded. Office of Strategic Services Report 113, compiled post-war. Enemy unaware of centimetric principle. Effective counter devices impossible within available resources. 273 Wing Bulletin. Instruments primary. Visual acquisition secondary. The statements captured strategic reality. Japanese forces could not counter what they did not understand. Understanding required technical foundation Japan lacked. Foundation required industrial capacity and scientific knowledge. Both were absent. Countermeasures remained ineffective because underlying technology was unavailable. Allied capability improved continuously. Equipment upgrades, procedure refinements, personnel training, maintenance improvements. Each marginal gain accumulated. Japanese countermeasures lagged structurally. Not unit issue, industrial limitation. Strategic technology choices made years earlier determined wartime capability. Choices favoring other priorities left radar development underfunded. Underfunding created capability gap. Gap became operational disadvantage. Disadvantage contributed to defeat. In the War of Waves, silence protected those who mastered frequency. British radar operated on wavelengths Japanese could not detect or disrupt. Emissions were directional. Power was sufficient. Frequency was unknown. The combination made detection difficult and jamming impossible with available technology. Even if Japanese forces detected British radar, they lacked means to interfere effectively. The advantage was comprehensive. Interception rates above 80% meant most raids faced fighters. Bombers dropped ordnance early or aborted missions. Targets received fewer bombs. Damage decreased. Effectiveness plummeted. The offensive capability degraded without proportional loss of aircraft. Deterrence through presence created strategic effect exceeding direct attrition. Enemy unwillingness to accept losses curtailed operations as much as actual kills. Fighter crews refined tactics. Experience taught optimal approach angles. Radar limitations became known. Procedures adapted. Training incorporated lessons. New crews learned from veterans. Institutional knowledge grew. Capability increased. The learning curve was steep and sustained. Improvement continued throughout the campaign. Final effectiveness far exceeded initial performance. Potential realized through repetition and refinement. Japanese researchers documented their attempts. Post-war examination revealed extent of effort and limitation of results. Allied investigators found Japanese countermeasure programs minimal and ineffective. The gap confirmed Allied technical superiority. Superiority translated to battlefield advantage. Advantage delivered victory. Technology shaped outcome. The wave war was won before it started. Industrial and scientific foundations determined result. Combat validated what capacity predicted. October 1944. Burma skies. Theater-wide assessment. Sector plotting board showed fewer red arrows weekly. Raid count fell below 5 per week. Pilots reported more aborts than combats. Japanese offensive air operations approached collapse. The network achieved its purpose without final decisive battle. Accumulation of effects created strategic result. General William Slim commanded 14th Army. 224 Group RAF provided air support. Japanese air staff faced impossible situation. Navigational confidence collapsed. Raids curtailed. Crews diverted to ground support or withdrawn. Redeployment reflected recognition. Offensive operations over Allied-controlled territory were unsustainable. Losses exceeded replacements. Results failed to justify risk. Operational calculus turned decisively against continuation. Radar intercept data showed 1,224 sorties plotted during the campaign. 1,019 engaged by controllers. 612 confirmed destroyed. Allied operational losses 38 aircraft across the period. Loss ratio exceeded 15-1. Sustainability favored defenders overwhelmingly. Maintenance availability remained high. Sortie generation continued. Pressure was constant. Enemy forces had no respite. Strategic Air Section Report Number 42. Enemy offensive air capability neutralized by loss of navigational confidence. The assessment captured mechanism. Physical destruction was significant but incomplete. Psychological effect was decisive. Crews unwilling to fly into effective defense. Commanders unwilling to waste scarce resources. The deterrent achieved strategic paralysis. General Slim wrote in Defeat into Victory. The unseen network gave us eyes when the monsoon took sight. The metaphor was apartment radar replaced vision. Electronic detection overcame meteorological limitation. Technology adapted to environment. Environment no longer dictated operational tempo. The advantage was profound and sustained. Persistent radar control converted to strategic effect. Air superiority without proportionate aircraft buildup. Ground operations gained freedom of movement. Supply lines functioned without constant air attack. Forward airfields operated with acceptable security. The enabling effects were broad. Air superiority was foundation. Foundation supported offensive operations. Operations delivered territorial gains. Gains accelerated Japanese collapse. The causal chain was clear. The decisive variable proved to be information, not aircraft totals. Allied forces fielded fewer fighters than hypothetical force without radar would require. Detection and direction multiplied effectiveness. Fewer aircraft accomplished more. The lesson was transferable beyond Burma. Information advantage provided force multiplication. Force multiplication enabled economy of effort. Economy freed resources for other uses. Optimization across domains delivered strategic advantage. Japanese air staff recognized defeat. Post-war interrogations revealed understanding developed too late. The mechanism remained mysterious during combat. Attribution to weather, mechanical failure, and bad luck prevented effective response. True cause remained hidden by classification and operational security. Recognition came after surrender. Understanding could not reverse outcome. The campaign was decided. October marked effective end of Japanese offensive air operations over Burma. Raids continued sporadically. Intensity never recovered. Air superiority remained Allied for duration. Ground campaigns proceeded with air support. Japanese ground forces lacked equivalent support. The imbalance contributed to defeat. Air power was decisive. Radar enabled air power. The chain held. Outcome followed from fundamentals. Fundamentals were technological and organizational. Both derived from industrial and scientific capacity. Capacity determined capability. Capability shaped history. May through August 1945. Rangoon, Southeast Asia Command radar drawdown. Technicians inventoried crates. Masts lowered. Logbooks boxed for shipment. A clerk stamped RD/END/45 on final audit. The network dismantled. War ended. Equipment repurposed or destroyed. Personnel redeployed. The emergency apparatus stood down. Expectation among planners. Temporary wartime expedients, soon obsolete. Reality. Service life exceeded 1,100 hours per set average, 40% beyond European estimate. Procedures codified for civil use. Temporary became foundation. Expedient became standard. Wartime necessity drove innovation. Innovation proved durable. Lessons learned transferred to peacetime applications. 160 sets transferred to Malaya and Netherlands East Indies for post-war air defense. Others cannibalized for spare parts. Many buried due to humidity damage beyond economic repair. Equipment designed for Britain weathered Burma. Not all survived. Survival rate exceeded predictions. Performance validated investment. The network delivered value exceeding cost. Communications personnel redeployed to civil aviation and post-war military systems. Training received during war became qualification for peacetime employment. Skills transferred. Experience valued. Careers built on wartime service. The human capital developed during emergency found post-war application. Investment in training paid dividends beyond immediate military need. SAC file RD/END/45. Satisfactory endurance. Procedures to inform post-war air traffic control. Final site log. All lines recovered. Destruction of unserviceable valves completed. The documentation was mundane. Significance was profound. Wartime improvisation formalized into post-war doctrine. Radar transitioned from secret weapon to standard infrastructure. Classification lifted gradually. Technology proliferated. Commercial aviation adopted radar. Military establishments worldwide incorporated lessons. Burma experience informed development globally. The empire contracted after war. Territory returned to independence. Political structures changed. Technical knowledge persisted. Manuals, technicians, and procedures diffused through post-war institutions. Indian civil aviation inherited equipment and trained personnel. British doctrine influenced air defense systems. Former enemy Japan rebuilt with Allied assistance, incorporating radar from inception. Technology transferred through multiple channels. Influence extended beyond political boundaries. Demobilization proceeded systematically. Priorities shifted from combat to reconstruction. Resources reallocated. Personnel discharged. The vast apparatus of war contracted rapidly. Within months, network that dominated Burma skies existed only in records and memory. Physical infrastructure dismantled. Institutional knowledge preserved in documents and minds of veterans. The transformation from war to peace was swift and total. Yet the principle endured. Detection range and warning time remained fundamental to air defense. Cold War systems built on foundations laid in Burma. Continuous improvement proceeded from wartime baseline. Technology advanced. Procedures refined. But core concept persisted. Early warning enabled effective defense. The lesson was universal. Application global. Burma proved concept under harsh conditions. Proof validated approach. Validation justified investment. Investment delivered capability. Capability shaped post-war world. The network's physical presence ended. Its influence continued. Former enemies adopted former adversaries' methods. Victors built on wartime success. The diffusion of knowledge accelerated. By 1950, radar was standard for civil and military aviation worldwide. The secret weapon became common tool. Uncommon remained the conditions under which it first proved decisive. Burma monsoon was unique, yet principles discovered there applied universally. The legacy was technical and doctrinal. Both endured decades beyond the war that created them. 1946 to 1950. London Air Ministry Retrospectives. Indian Civil Aviation Records. A shelf copy of Radar in the Far East carried Air Vice Marshal Sir Roderick Hill's assessment. Adjacent files documented Indian adoption of radar at Bombay, Delhi, Calcutta by 1950. The transition from wartime secret to peacetime standard proceeded rapidly. Technology once classified became public. Applications once military became civil. Knowledge dispersed. Expectation among post-war planners. European innovations define air control systems. Reality. Asian theater practices, refined in monsoon conditions, shaped procedures and training. Burma experience informed standards. Tropical adaptation became baseline for global deployment. Lessons learned in jungle transferred to deserts, mountains, and Arctic regions. Environmental adaptation proved generalizable. Techniques developed for humidity applied to dust, cold, and heat. Innovation under constraint yielded robust solutions. Air Ministry archives documented campaign outcomes. 224 group records transferred to historical section. Technical reports assessed equipment performance. Personnel records tracked careers of key contributors. The documentation was comprehensive. Future historians would find sources. Analysis would follow. Understanding would deepen over decades. Immediate post-war period focused on demobilization. Historical assessment came later. Both were necessary. Both occurred. Government of India Civil Aviation inherited trained personnel and functioning procedures. Bombay, Delhi, Calcutta airports installed radar by 1950. Approach control, terminal control, and en route surveillance adopted wartime methods. Civilian controllers learned from military veterans. Continuity preserved expertise. Safety improved. Capacity increased. Commercial aviation grew on foundation built during war. The connection was direct and documented. Japanese technical archivists examined captured Allied equipment post-war. Analysis revealed extent of technological gap. Understanding came too late to affect outcome. Knowledge informed post-war reconstruction. Japan rebuilt aviation industry with radar from inception. Former enemies became post-war partners. Technology transferred through occupation and assistance programs. Development proceeded rapidly. By 1950s, Japanese radar industry was competitive. The transformation was remarkable. Foundation was Allied technology and doctrine. Application was Japanese engineering and manufacturing. Synthesis created new capability. Air Vice Marshal Sir Roderick Hill wrote, "It was the radar station more than the airfield that defined the battlefield." Japanese archive note, December 1945. The enemy observed us when we could not observe ourselves. The assessments from opposite sides converged. Information advantage was decisive. Observation enabled response. Response denied enemy freedom of action. Denial created opportunity for offensive operations. The causal chain was universal. Application in Burma demonstrated principle. Principle applied globally. Burma Air Campaign showed consistent chain. Industrial capability, deployable radar, disciplined communications, warning time, interception probability, reduced enemy sortie effectiveness. The human cost and effort resided not only in aircrew but in technicians, line parties, and telephonists whose logs and procedures outlasted jungle sites. The monsoon did not blind radar. It blinded those without it. Campaign's most durable measurement was detection range and minutes of warning. Numbers that continued to govern skies long after guns fell silent. Technology evolved. Ranges extended. Warning times increased. But fundamental principle remained unchanged. Early detection enabled effective defense. Burma proved it. Post-war world adopted it. Legacy endured. Memory honored those who made it possible. History recorded achievement. Understanding deepened over time. Respect remained constant. The war in Burma demonstrated what many thought impossible. Radar functioned in monsoon conditions. Equipment adapted to tropical environment. Networks operated across difficult terrain. Personnel sustained operations under harsh circumstances. Technology overcame nature. Organization multiplied capability. The result was air superiority that shaped campaign outcomes decisively. Numbers told part of the story. 612 Japanese aircraft destroyed. 38 Allied lost. Loss ratio 15-1. Sortie generation sustained. Maintenance availability exceeded 90%. Warning times measured in minutes where previously measured in hours. Detection certain where previously uncertain. Interception probable where previously rare. Statistics captured transformation from vulnerable to dominant. Human dimension completed the picture. Operators at scopes tracking echoes. Controllers computing vectors. Pilots flying intercepts. Technicians maintaining sets. Line parties repairing cables. Fuel crews moving supplies. Telephonists relaying plots. Each role critical. Each person necessary. Collective effort delivered result. Individual contribution enabled success. The network was human as much as technological. Integration of both achieved outcome neither could alone. Industrial foundations supported everything. British factories produced equipment. Shipping delivered it. Workshops adapted it. Supply chains sustained it. Training programs prepared personnel. Doctrine guided employment. Organization structured effort. The apparatus was vast. Coordination was essential. Effectiveness required all elements functioning. Weakness anywhere created vulnerability everywhere. Strength derived from comprehensive capability across domains. Strategic lesson extended beyond Burma. Information advantage provided force multiplication. Detection and direction enabled economy of effort. Fewer aircraft accomplished more with proper guidance. The principle applied to air defense proved in combat became foundation for post-war systems. Cold War air defense built on wartime experience. Civil aviation incorporated military procedures. Technology civilian and military shared common roots in Burma jungle. Enemy perspective revealed what occurred. Japanese forces attributed losses to weather, mechanical failure, navigation error. True cause remained hidden. Radar was classified. Network was secret. Electromagnetic detection was invisible. Understanding came post-war. Recognition could not reverse defeat. The invisible shield remained invisible to those it opposed until too late. Secrecy was weapon. Classification preserved advantage. Operational security prevented countermeasures. Memory honors those who served. Names recorded in unit histories. Logs preserved in archives. Photographs show faces. Documents record actions. The individual stories are many. Collective achievement is singular. Air superiority over Burma was won by thousands working in coordination. Technology enabled. People delivered. Both necessary. Neither sufficient. Integration decisive. The monsoon came every year. Rain fell in sheets. Clouds hung low. Visibility approached zero. Yet operations continued. Detection was constant. Warning was timely. Interception was probable. Nature no longer dictated tempo. Technology adapted environment to operational requirements. The reversal was profound. Implications extended decades beyond the war. Final accounting showed network delivered value exceeding cost by substantial margin. Investment in radar, infrastructure, training, and maintenance paid dividends in air superiority. Air superiority enabled ground operations. Ground operations delivered victory. The chain held from technical decision to strategic outcome. Each link critical. Overall result was greater than sum of parts. Synergy was real and documented. Burma Radar Network proved that technological advantage, properly exploited through disciplined organization and sustained maintenance, could overcome environmental challenges and deliver decisive military advantage. The lesson was universal. Application was specific. Success required both. History recorded achievement. Understanding informs present. Memory honors those who made it possible. What is your perspective on this part of history? Share your thoughts in the comments. because every memory and reflection helps keep the past alive.